of movie user ratings with lots of missing values. And they invited people to train a model to predict some of the missing values that were held out. And so this paper is a description of the winning approach to the Netflix challenge, which was a latent factor model. And so this paper actually, in some ways, put latent factor models on the map in the machine learning community as sort of one of the most powerful approaches you could use in this type of regime. In this type of problem, where you have like user movies or faces by pixels, these multi-dimensional observation matrices, they come up a lot in many applications. So this particular visualization from this paper, the authors put the Wizard of Oz in the middle. They centered everything around the Wizard of Oz. They visualized two of the latent factors, and they looked at where other movies are relative to the Wizard of Oz and they compared it, right? So over here we got things like action style movies, right? And over here we have, I actually have a hard time interpreting that, but certainly not action. Some of these are hard to interpret when you embed it, when you project it on a two-dimensional visualization. They certainly make more sense if you're looking more dimensions at a time, which is hard to visualize, of course. But okay, so just a recap of collaborative filtering. The goal is you're given this matrix of user item ratings, most of which is missing. And the goal is to learn a model that can predict the missing entries. And you do this by, and the latent factor approach does this by making the assumption that there exists a low-rank subspace or a low-rank manifold that captures the variability of describing different users and items. And what this amounts to in practice is you learn a feature vector U for every user, U sub I for every user, a feature vector V for every movie, V sub J, and for every observation that you do observe in the training set, you want to make sure that the linear model using those two feature vectors is a good approximation of the data that you observe. And that's it. And it has connections to singular value decomposition, low rankness, and everything that we've talked about in the first 45 minutes of lecture. Yeah?
What's the percentage of missing values in the total?
It can obviously depend, right? And in practice, it's often very skewed. So the observation frequency often follows a power law distribution. So there's some very popular movies, and then most movies are not that popular, right? I think I talk about later how to deal with the case where you have very, very, very few observed entries. Like some movies are only rated by a few users. So in general, I think like a popular movie like what's a recent movie like Hunger Games, right? Has probably been rated by a substantial fraction of the users on Netflix or whatever movie service. Maybe not Netflix doesn't have it, but maybe I don't know. 30%, 40% are rated, or maybe even 20%, right? It's usually less than, it's usually noticeably less than 50% of the users. But even if 10% of the users rated, if 10% of the users rated Hunger Games, and then a somewhat different 10% but with overlap, right, rated some other movie like the Hunger Games, then that's enough. There's enough overlap to learn that these users like a user that likes one should like the other. Yeah.
Is there a relationship between these like alternating optimization and like the EM? Because it sounds conceptually similar. Like one where you're trying to like optimize movies, then users and movies and users. The other one.
Yeah. So EM is also an alternating optimization approach, but this is not EM.
Okay. So there's different ways of doing the same thing.
Let me think before I. Hold on, can you interpret this as EM? No, you can't interpret this as EM because in EM, the idea is one step in the alternating observation is about estimating latent values.
That's kind of what you're doing, because you're doing the regression, then regression, then regression.
I suppose there is a way to interpret this as EM, but if you talk to people in machine learning, when they talk about EM, they mean something different typically. They mean like you have some model that makes inference about late values, and from that you train the parameters of your model. Here, there's a symmetry between the two that's so symmetric that it's not the way people typically think about when they think about EM. I suppose there's a way to pose this as EM. I suppose so. I have to think. I would guess there probably is.
Okay.
But if you sort of say this is EM, most people in machine learning would just give you blank stares.
Okay.
That's not typically what they think of. They think about things like topic models, and hidden mixture models like Gaussian mixture models or HMMs. They do EM nothing. There's a clear asymmetry there. Right?
Yeah.
Okay, so just an aside on multitask learning. So, one can also view this type of collaborative filter problem from the lens of multitask learning, right? So in multitask learning, we want to learn more than one task. If you think of each user as a task, like I want to learn a model of what this user likes, then you could think of the Netflix problem as a multitask learning problem, where I have one task per user. And I want to learn a model jointly over, or I want to learn models over every task simultaneously by maybe assuming that the users have things in common. So for example, if I had, some X, so this is the standard multitask regression problem, where we have features over items, and we have M users, right? And we want to learn a model for every user. We want to learn a model for every user, in this case a linear model, such that the linear model for this user this should also be indexed by M. For this item, the regression value for this item for this user is close, and then we have some regularizer over all possible users. Okay, so one question in this type of problem, and, it should be clear that there's some connection to collaborative filtering. But I'll make that connection a little bit more explicit. But let's just think about this formulation of the problem. How do we regularize, right? So here, if we use the standard L2 norm, right, which is basically the Frobenius norm, the squared Frobenius norm, right? Then this is just the sum of squares of every entry in W. So you can decompose it additively by task, by user. And so it actually decomposes into M-independent estimation tasks. So we're not actually taking advantage of the fact that this is a multitask problem. We're not actually sharing information between users. Right? If the amount of Y's that we observe for every user is relatively little, this particular formulation doesn't actually share the information between tasks. Another way that we can regularize is not use the Frobenius norm, to use the trace norm, right? Now we induce that the entire task parameter matrix has low rank across all tasks, right? So now you can no longer decompose this objective function additively across every task, because this thing ties them all together, right? Okay. So here's another way to do it. So recall that this is equal to this, right? For sufficiently large U and V. So instead of optimizing over the trace norm W, we can optimize over two matrices U and V. But now, so we observe X and Y for X, the features of some item, and Y, the ratings that user M give to item I. And again, there should be a superscript M here. Apologies for that. And so instead of regularizing W, instead of learning a parameter matrix W like this, and regularizing using the trace norm, it's equivalent, more or less, to have two parameters, U and V, regularize the squared Frobenius norm of the two, and then do this, right? So now, what is this? We're learning we're learning a transformation of V that transforms our feature vectors X into some lower dimensional X prime that's lower dimensional than the raw features of X, and then we're learning a low dimensional model U, right? So the raw dimension of X, of each X is D, and then v is d by k, or k by d, then this projection will transform each x into a k-dimensional vector feature, a k-dimensional feature input. And so now instead of having to learn a d-dimensional model per user, we're going to learn a k-dimensional model per user, per task. Right? So what does this mean? This basically is saying we have a bunch of different tasks. We assume that the parameter vector for every task is it has a low-rank structure across tasks. So one way to represent that equivalently is to find a common low-rank projection of the raw input features into this low-rank projection, and then learn a low-rank model per task in this common low-rank projection of the raw input features.
Is there like an implicit constraint on U and V and they have to still be orthogonal? Or
No.
Okay.
No, in here, no.
Okay.
If y was completely observed, I believe the optimal solution will have them be orthogonal.
Oh, so it'll have to be to enforce. You don't need to enforce.
If y was fully observed, I don't quote me.
Okay.
I think that's true.
Okay.
But here, no. Did you have a question?
Yeah, I'm trying to remember, don't the trace norm and the Frobenius norm have the same value?
No.
I thought that if you do a cyclic permutation of matrices.
Right, they do. The trace of A times B is equal, ABC is equal to the trace of BCA,
Right.
but the trace norm and Frobenius norm take the trace of different things. The Frobenius norm is the square root of trace, the Frobenius norm of x is the square root of the trace of x transpose x. The trace norm of x is the trace of the square root of x transpose x. So the square root is inside the trace as opposed to outside the trace. So they're actually different. Yeah. Okay, so in this, so in the problem where we model w completely as, where we regularize w using the squared Frobenius norm, so it decomposes actively into m tasks. This has d times n parameters, right? Where n or m, I guess. N is the number of tasks, and d is the dimensionality of the raw feature input. In this version of the problem, right, we have d times k plus n times k parameters, where d is the raw dimensionality of x, k is the projection of v, because v is d by k, and then so this is v, and then the U matrix is n by k, right? So this is much smaller than d times n if k is small, right? So why is this good? Well, the whole premise of multitask learning is that if we assume that the different tasks, in this case different users, are somehow related to each other, right? Then we should be able to share data between them in order to learn a more reliable model if we have very little training data per task, right? So if you only need to estimate this many parameters, it is statistically more efficient to estimate these many parameters reliably than to estimate these many parameters reliably, right? So you'll get a more accurate model with this optimization procedure, with this model, with this type of model, if the low rank assumption across tasks is an appropriate assumption. And it often is in practice. Right? But of course, this is an assumption. In order to get this benefit, you have to make an assumption. Just to summarize, this is the multitask learning objective that is, this is one version, there are different versions of course. You can reduce this to collaborative filtering if each x is just an indicator vector, right? If each x is an indicator vector of the item ID, right? So this is like in the feature-free case. If we don't have any features, then then this v will become a k by the number of items, right? Because then this feature vector will be of dimension equal to the number of items. Right? So this is how we reduce this version of multitask learning back to collaborative filtering. Right? This is actually a generalization of collaborative filtering. And this is how you deal with the problem case where you have some movies that have very, very few ratings. If you have some other features about the movie, like is it starring Jennifer Lawrence, right? That's her name. Jennifer Lawrence, that's a feature. You could treat that as a feature. Now, now you could say this user likes movies by Jennifer Lawrence. This is a feature that can generalize across movies. So this X, so in general, this X feature can have standard features about movies plus their identity. And if you don't know anything about the specific movie, you can still learn a model about the generic features of the movie. So the two can be combined. And this is actually how people deal with the fact that some of the movies, so this matrix can be super, super sparse for some movies. And the same can be true for users. So do I talk about, I think I'll talk about this next, in a couple slides. How you can do this for users as well.
Well, aren't you kind of hoping that like if that feature is meaningful enough, it would pop out anyway? Like.
Well, if this is all you have, that feature doesn't exist. Oh, you mean
But I'm saying, yeah.
one of the dimensions of V?
Yeah, like when you expect like if a strong predictor is that the sort of people like Jennifer Lawrence movies, like then wouldn't you expect that to pop out?
Only if one of the dimensions of V correspond, only if magically, not magically, but serendipitously, coincidentally, when you solve this optimization problem, one of the V's corresponded whether or not Jennifer Lawrence appeared in this movie or not. And the problem with that is that I could do this for any actor, many actors, right? And suddenly now it's like this huge high-dimensional estimation problem. But if you handcrafted features, then that actually makes the estimation problem more well-posed and statistically more efficient. If you can handcraft good features, it always makes the problem statistically more efficient.
Yeah.
But it's not always, but
yeah.
typically.
But I mean, I guess my intuition is that the idea of these things is they're supposed to, if they're working well, they're going to pick out the important features that are.
Right, but it can also do the following, right? Let's say, I'm going to really embarrass myself with these naming actors. Let's say the movie has the term Star Trek in it, or there's the term Star Wars in it, and then that's a feature. It has the word Star Trek in it, or it has the word Star Wars in it. We can actually learn to project Star Trek and Star Wars onto a common dimension using V. Right? So those are the types of tricks we can do. Now that trick is much easier to do if you had a feature that says Star Wars and a feature that says Star Trek. You can even imagine nested layerings of these projections. Now suddenly we're talking about deep learning, which I'll get to next week. But here's just one projection. And so typically you want to use features. So yeah, these two problems, this is a latent factor model for collaborative filtering, latent factor model for multitask learning. Very, very similar. The key difference is that in collaborative filtering, we just assume that we learn this V, which has dimension k by the number of items. And here it's k by the dimensionality of the representation of items. And the representation of items could scale with the number of items, or it cannot. And so this is a more general formulation in many ways. Okay, so you could do the same for the user side, right? There's no reason why we can't use features of users. Like when a brand new user comes to Netflix or any of these recommender systems, we may have some information about, their demographics like age, gender, location, right? Things like that. And we can actually use that to help make better predictions, even if we haven't seen a single recommendation by this user before. So in this problem, right? If a matrix, if a row of Y was completely empty, we're hopeless, right? If we've not observed anything about a row of Y for a user, this U must be 0 by regularization, right? So we have to, so in this formulation, also this formulation, we must have observed at least one data point for this user in order to learn anything, right? Otherwise, by regularization, we just learn 0. This is called the cold start problem in recommender systems, right? If we don't already have some data about the user, we can't do anything. We can't make any meaningful personalized recommendations. One way to get around that is to say, well, we can measure some features about users, and hopefully other users with similar features share some commonalities with this user, even if not all, right? And so you can encode that with Z. So now Z can encode the identity of the user. So Z can be, the dimensionality of Z can scale with the number of users in your data set, and Z can encode not only the identity, but other some sort of general demographic information, right? And so we do the same trick as on the movie side as user side. This is called a general bilinear model. In this particular case, it's a low latent factor bilinear model. A general bilinear model has a single W here, but we assume that it's low rank. So bilinear models, right here. So the only main difference is the dimensionality of the UV matrices, right? Dimensionalities of the UV matrices. So here, and so in collaborative filtering, we don't have any features, so it has to scale with the number of users and the number of movies. Here, on the right-hand side, it scales with the number of features, which can also scale with the number of movies, or it cannot. And then this general form, this is the most general form. So it gives you the most flexibility, and it generalizes the previous two. Okay, so the story so far, latent factor models reduces the SVD if there's no missing values. We have, we can use these features, which in the simplest case are just indicator features of which movie and which user it is, in which case this is standard collaborative filtering. And the basic intuition is that we're projecting these high-dimensional data points into a low-dimensional space where they can be estimated more reliably. Any questions? Yeah?
In this system, when you want to add a new user, how do you initialize the vector ZI?
So ZI, I'm sure every company does it a little bit differently, but sort of I would imagine the standard approach, the basic standard approach is you would actually decompose this additively into two components. One that's just bilinear on the, one way to do this is just this bilinear in the features and then bilinear in the identities. That would be one way to do it.
And then when you add a new user, you have to change the vectors for all the...
So typically you don't. Typically you hold V fixed. So for example, right, so typically you can, if you have a lot of data, you can hold V fixed and just estimate U for when new users come. And then let's say once a week we re-estimate the whole model and get a new V. That would be a typical thing that people would do in practice. You would not estimate the whole thing from scratch. Whenever a new user comes, you would not estimate U and V from scratch, although you'll get slightly different answers, but people typically don't do that. It's just too computationally expensive. And so you just hold V fixed, estimate U, and then every week re-estimate the whole model. I don't know exactly how these companies do it, but that would be sort of the principle. They could do it every night, like once a day, I don't know. But they definitely would not do it every second. Like whenever a user clicks on something, rates something, they definitely would not do that. Yeah. Okay, so the second topic, much shorter, is non-negative matrix factorization. So going back to the SVD and PCA, if we look at this data set, right? So in this data set, by sort of construction in this toy example, all the data points are in the positive orthant of the raw feature representation, which is, by the way, true for the eigenfaces data, but all the pixels are non-negative. And so, if I squint, and I do a mean centering, then the purple might be what PCA or SVD gives me, right? Because it somehow tries to capture the directions of most variability, but it's really not that great, right? Somehow there seems to be one sort of dimension here and one dimension here that really captures most of what's going on, right? But of course, you can't get this using PC or SVD because the dimensions that you learn in PC and SVD have to be orthogonal to each other, right? And so is there a better way to model data sets that look more like this? Right? And that's where non-negative matrix factorization comes in. So we're going to assume now that Y is non-negative. And the fact that it's non-negative has some sort of semantic meaning. And then we're going to do the same type of factorization into U and V transpose. But now, and they'll also be referred to as latent factors. But now we're going to think of U and V also as non-negative, right? So what does this look like if we apply this to the eigenfaces problem? So this is CS155. in the case of non-negative face spaces, or face spaces. So this is Emily and Armand again. And so here how it works is there is no mean face, right? There's the initial face is completely black. It's completely dark. Every pixel is black. And then we just add components, add these components, and multiply it by the coefficients for, so again, U, each of these is a U, and then every column of V transposed is Emily's coefficients, Alma's coefficients, each one of your coefficients. And they're all non-negative, and the base case is just completely dark, so there's no notion of a mean face. And so we see that, these two correspond, so this one certainly corresponds to faces that are a little bit more rounder, sort of more pointed at the chin. Here it's really focused on sort of getting this part of the face. Here it's focused on people who have bigger foreheads maybe. And then here it's again, I guess this is a lateral shift maybe. And by the way, these images are not in are not in false color. The black really means black, and not black really means not black. And then the red coefficients are Emily's coefficients, and the blue coefficients are Alman's coefficients. So for example, so Alman has hair over his forehead, so some of the bases that puts a lot of illumination or non-black color on the forehead, he has low weights. Yeah.
How do you sort the features?
How do I sort?
Yeah.
You mean the 12 faces?
Like for example, you want to pick the top 12 features, right?
Yeah.
So how do you sort them? Because in the
You have to, right, so in SVD you just you can compute every possible K and just pick the top K later. In non-negative matrix factors you can no longer do that. You have to choose a K beforehand. So in singular value composition, if you take the top K versus the top K plus 1, the top K is a subset of the top K plus 1. By construction, by proof, in non-negative matrix factors, that is no longer true. So if you pick K equals 12 versus K equals 6, the bases could look very different. So you have to choose K beforehand and then rerun over and over again. And just to compare this to the sort of eigenface basis from the previous lecture where you have a mean face, and now this is in false color where black is negative and white is positive. And the coefficients can be positive or negative, and this is adding and subtracting from the mean face. So a couple of things should stand out to you. One is that this should actually be, I mean, it's a little blurry because I had to manually crop these myself, but it should still be quite clear that these phase bases are more visually interpretable than these, right? Because this one somehow superimposes both the positive portion and the negative portion onto the same image, right? And if you were to visualize this using the same image, and that's just hard to interpret. Whereas this one's like, well, black means no contribution, and not black means some contribution, right? So, of course, the U's and V's that you estimate for the non-negative matrix factorization are no longer orthogonal, right? And before the non-negative case, and so they don't satisfy all the nice properties of SVD and the bases you learn from SVD and PCA. So in order to reverse the transformation, if you wanted to reverse the transformation, you have to use something like the pseudo-inverse to reverse the transformation. Okay, so what is the objective function for non-negative matrix factorization? So we have a matrix Y, and here we're going to assume that Y has no missing values. We'll relax that in the last part of this lecture. We're assuming Y has no missing values, so it's a fully observed matrix of pixels by people. And then we want to find a U and V, both non-negative, such that each entry, each pixel person entry, is well reconstructed by UI transpose Vj. Right? And so this loss function could be squared loss. It could be this notion of a generalized relative entropy, which is basically unnormalized scale divergence. And the main difference between these two is that this one penalizes the ratio, basically. That's the main qualitative difference. whereas this one penalizes the square distance. So what does that mean? That means that if A is somewhat large, right, then B cannot be too small, be too close to 0, because this is a pretty big penalty. It's basic elements. Whereas here, it's just L2 distance, so it's just an additive distance. And so which one you want will depend on your application. So let's say the PCA finds the best orthogonal basis faces, can be negative, coefficients can be negative, trickier to visualize. With respect to squared error, it gives you better reconstruction with fewer basis faces, right? Because that's just by definition what the SVE tries to go for. Non-negative matrix factorization tries to find the best set of non-negative basis faces with non-negative coefficients, and they're often easier to visualize because it's the dark parts of the image is just that, it's no contribution, then some contribution. Of course, because they're not orthogonal, they can require more bases for good reconstructions. Okay? So that's the trade-off. Non-negative latent factor models is basically just a simple, simple extension where U and V have to be non-negative, and then there's some loss function that can be either squared loss or relative entropy, both of which are differentiable. Okay, so the last part of the lecture is on a quick application to using non-negative latent factor models for modeling NBA gameplay. So this is some work that I did when I was at Disney Research. So imagine that we had data that can say, we can estimate where players like to shoot the ball by observing sort of entries of where people like to shoot the ball. And so we can estimate this model. If you follow basketball, this is the shooting chart of Tim Duncan, who plays for the San Antonio Spurs. So we can model something like this. And it looks, it's really great for someone like Tim Duncan who plays a lot. But of course, most players haven't played that. We have the same sort of missing values type of problem, right? And so in order to model players that have not even played that much, we took a latent factor modeling approach, non-negative latent factor modeling approach. And so you could think of this matrix as M as the number of players in the NBA, and D as the number of locations on the court. So here D equals 2,000. So you can think of this, rather than eigen faces, it's eigen shot types, right? So D is the number of locations on the court, M is the number of players. And because we haven't really observed many players play, we don't know whether or not they like to shoot from a certain location on the court because we just don't have that much confidence because we haven't made that many observations. So we make the standard low rank assumption where we assume that this matrix of shot charts can be decomposed into a non-negative matrix factorization of player factors and location factors, such that how likely someone is to shoot from a location is simply the inner product of this guy and this guy, right? Where B is the player and L is the location. So for k equals 10, how many people here follow basketball? Okay, a few. Not as many as I was hoping for, so maybe this is kind of boring for most people. You can imagine this is soccer instead, if it pleases you. We've done the same. We've done some analysis for soccer. So here we're visualizing, so D equals 2,000, so we're visualizing every row of this L matrix here. And so you can think of these as features that we learned from where people like to shoot on the court. The corner three, the wing three, left wing, right wing, free throw area, high post, left low post, right low post, etc. And then now every player